Hey there and welcome. Today, we're going to jump into a field that, it sounds super complex, but it's fundamentally changing how we create the world around us. We're talking about computational thermodynamics, which is this really revolutionary way to invent new materials, not in some lab with beakers and burners, but doing it all inside of a computer.
Okay, so just think about it for a second. How do you invent the next breakthrough alloy for a jet engine? Or a lighter, stronger metal for a new electric car? For like decades, the answer was a ton of mixing, melting, testing, a process that could take years, even decades. But what if you could predict exactly how a new material would behave before you even made it?
Well, that's the whole game right there. That's what computational thermodynamics does. The best way to think about it is like a weather forecast, but for materials. Instead of predicting rain or sun, scientists are using these incredibly powerful computer simulations to forecast the properties of a material under all sorts of conditions. You can imagine, this saves a ridiculous amount of time and money.
All right, so here's how we're going to tackle this. We'll break it down into 5 key parts. We'll start with that main idea, that weather forecast. Then we'll check out the big breakthrough that kicked this all off. After that, we'll see what it actually produces, uncover a huge challenge the whole field is facing right now, and finally, look at the really exciting future of designing materials literally atom by atom.
So, let's dig into that first piece of the puzzle. How do you actually create a forecast for something that doesn't even exist yet? Well, it all comes down to a really fundamental principle in physics.
At the end of the day, the whole system is built on finding the most stable state for any mix of elements. Just like a ball will always roll to the bottom of a hill to find its lowest energy state, materials do the exact same thing. They're always trying to arrange themselves in whatever configuration has the absolute minimum possible energy. And in the world of thermodynamics, that sweet spot of lowest energy has a name: Gibbs free energy. So by calculating this for countless possibilities, computers can pinpoint the most stable and, because of that, the most useful new alloys.
Now, you got to remember, this wasn't always possible. It took a massive breakthrough, a completely new way of thinking that turned all these theoretical calculations into a practical tool engineers could actually use. And that brings us to the CalFad revolution.
So CalFad, this is the engine that makes the whole thing go. It stands for Calculation of Phase Diagrams, and it's the method that lets scientists build these material forecasts. You can really think of it as the operating system for computational materials science.
And it's pretty cool to see how this all came together. The groundwork was actually laid way back in the early 1900s. But it was an American metallurgist, Larry Kaufman, who in the 1970s really pioneered the modern CalFad method. And after his breakthrough, groups like the SGTE Consortium came together to create these huge shared databases that really the entire field still relies on today.
Okay, so we have this powerful method called CalFad, but what does it actually make? What's the output that engineers can hold in their hands and use? Well, the answer is one of the most important tools in all of materials science.
CalFad is used to generate something called a phase diagram. And if you're a materials engineer, these diagrams, they're basically treasure maps. Seriously, they are absolutely crucial for understanding and designing new alloys.
And this is a fantastic way to think about it. A phase diagram is pretty much a recipe map. It tells you exactly what state, or phase, a material is going to be in at any given temperature and with any given composition. It can show you, for instance, if you mix this much iron with that much carbon and heat it to this exact temperature, you're going to get steel with precisely the properties you're looking for.
So how do they actually build these maps? Well, it's a pretty logical 3-step dance. First, scientists gather all the known experimental data they can find. Then, they create these mathematical models to describe the energy of every possible phase. And finally, they feed all of that into software that can take that data and predict the behavior of really complex alloys with lots of different elements.
Okay, but here's where things get tricky. This whole incredible, world-changing field, it's built on a foundation that might just have a huge flaw. It's a challenge so fundamental that some people are describing it in pretty stark terms.
Listen to this quote from a recent scientific paper. It really hits you. The author warns that fixing the problem could be like rebuilding a house due to a severely broken foundation. That's a serious statement. So what exactly is this broken foundation?
So what is this broken foundation they're talking about? Well, here's the deal. Almost every single CalFad calculation relies on one single, shared database of properties for pure elements, like pure iron or pure nickel. This is called the unary database. It's the starting point, the ground floor for everything else.
And if there are inaccuracies in that foundational data, those little errors can get magnified and ripple through every single calculation for every complex alloy built on top of it.
And that right there, that is why they call it the inverted pyramid problem. You've got this massive, incredible body of work, decades of material science, all balanced precariously on the tiny little point of that single unary database. And if that point is shaky, the whole pyramid is at risk.
But hey, scientists are problem solvers, right? They aren't just letting this sit. They are actively working on a solution, and it's a really cool one. It involves going back to the most fundamental principles of physics to rebuild that foundation from the ground up, literally, atom by atom.
The future is really about bridging the gap between two different ways of thinking. The traditional CalFAD method we've been talking about is top-down. It starts with real-world lab data. But the new kid on the block is ab initio, which is just a fancy Latin way of saying from the beginning. It's totally bottoms-up. It starts from pure quantum mechanics to calculate a material's properties from first principles. No experiments needed.
Now don't get me wrong, these ab initio methods are amazingly powerful, but they are also super slow and take a ton of computing power. So the goal isn't really to replace CalFET, it's to integrate the two. The real genius here is to use the super precise quantum calculations to go back and fix, to shore up that foundational unary database, making that whole inverted pyramid stronger than it has ever been.
And believe me, this isn't just some theory stuck in a lab. This work is a cornerstone of a massive, real-world effort called the Materials Genome Project. It's a huge initiative with a very clear goal: to discover, develop, and deploy advanced materials twice as fast. I mean, think about that. And solving this inverted pyramid problem is absolutely key to making that happen. And that kind of brings us full circle to this one. Really mind-blowing thought. For almost all of human history, finding new materials was this slow grind of chance and trial and error. But now we're right on the verge of being able to design them from the atoms up with total precision. So if we can map and predict any combination of elements on the periodic table, what amazing things are we going to build next?